Hello everyone, welcome to our channel AskPrep. In today's series on 11th grade chemistry, we will be studying chapter 2, Structure of Atoms in detail. Let's start the video. Discovery of electron, discharge tube experiment. In 1879, William Crookes studied the conduction of electricity through gases at low pressure. He performed the experiment in a discharge tube, which is a cylindrical glass tube about 60 centimeters in length. It is sealed at both ends and fitted with two metal electrodes. The electrical discharge through the gases could be observed only at very low pressures and very high voltages. Properties of cathode rays: travel in straight lines. Cathode rays travel in straight lines. Direction of travel: cathode rays start from the cathode and move towards the anode. Visibility: these rays themselves are not visible, but their behavior can be observed with the help of certain materials, fluorescent or phosphorescent, which glow when hit by them. Charge: cathode rays consist of negatively charged particles. When an electric field is applied to the cathode rays using a pair of metal plates, they are found to be deflected towards the positive plate, indicating the presence of a negative charge. The pressure of different gases could be adjusted by evacuation. When sufficiently high voltage is applied across the electrodes, current starts flowing through a stream of particles moving in the tube from the negative electrode cathode to the positive electrode anode. These were called cathode rays or cathode ray particles. Charge and mass of electrons. Through charge to mass ratio experiments, the charge and mass of electrons were determined. R.A. Millikan's oil drop experiment provided crucial insights into the charge of electrons, establishing it as a fundamental constant. The charge of an electron was measured to be negative 1.6022 times 10 to the power of negative 19 coulombs, while its mass was calculated to be 9.1094 times 10 to the power of negative 31 kilograms. Discovery of proton, anode rays. In 1886, Goldstein modified the discharge tube by using a perforated cathode. On reducing the pressure, he observed a new type of luminous rays passing through the holes or perforations of the cathode and moving in a direction opposite to the cathode rays. These rays were named positive rays or anode rays or canal rays. Anode rays are not emitted from the anode but from a space between the anode and cathode. Properties of anode rays. Charge: the value of the positive charge E on the particles constituting anode rays depends on the nature of the gas in the discharge tube. Charge to mass ratio: the charge to mass ratio of the particles is found to depend on the gas from which they originate. Multiple charges: some of the positively charged particles carry a multiple of the fundamental unit of electrical charge. What is a proton? The smallest and lightest positive ion obtained from hydrogen is called a proton. Mass of proton 1.676 times 10 to the power of negative 27 kilograms. Charge on proton plus 1.602 times 10 to the power of negative 19 coulombs. What is a neutron? The neutron is a neutral particle discovered by Chadwick in 1932. By bombarding thin sheets of beryllium with fast-moving alpha particles, he observed highly penetrating rays consisting of neutral particles which were named neutrons. Thomson model of the atom proposed model. J. Thomson proposed that an atom could be regarded as a sphere of approximate radius is 1 times 10 to the power of negative 8 centimeters, carrying a positive charge due to protons in which negatively charged electrons are embedded. Visual representation. In this model, the atom is visualized as a pudding or cake of positive charge with electrons embedded within it. Mass distribution. The mass of the atom is considered to be evenly spread over the atom according to this model. Drawback of Thomson's model. While this model could explain the overall neutrality of the atom, it could not satisfactorily explain the results of scattering experiments carried out by Rutherford in 1911. Rutherford's alpha particle scattering experiment. In 1911, Ernest Rutherford conducted scattering experiments by bombarding thin foils of metals, such as gold, silver, platinum, or copper, with a beam of fast moving alpha particles. The thin gold foil was surrounded by a circular fluorescent zinc sulfide screen. Whenever an alpha particle struck the screen, it produced a tiny flash of light at that point. From these experiments, Rutherford made the following observations. Most alpha particles pass through. Most alpha particles pass through the foil without undergoing any deflection. A few alpha particles were deflected through small angles. Very few alpha particles were deflected back through an angle of nearly 180 degrees. From these observations, Rutherford drew the following conclusions. Since most alpha particles pass through the foil without deflection, the atom must have a large amount of empty space. A small fraction of alpha particles were deflected at small angles, indicating that the positive charge is concentrated in a very small volume that repelled and deflected the positively charged alpha particles. This small dense core was later named the nucleus. The nucleus is very small compared to the total volume of the atom. Next up is Rutherford's nuclear model of an atom. The positive charge and most of the mass of the atom are densely concentrated in an extremely small region called the nucleus. The nucleus is surrounded by electrons that move around the nucleus at very high speeds in circular paths called orbits. Electrons and the nucleus are held together by electrostatic forces of attraction. Next is atomic number. The atomic number Z is the number of protons present in the nucleus of an atom. For example, the number of protons in a hydrogen nucleus is 1, and in a sodium atom, it is 11. Therefore, the atomic numbers are 1 and 11, respectively. To maintain electrical neutrality, the number of electrons in an atom is equal to the number of protons, atomic number Z. For example, the number of electrons in a hydrogen atom is 1, and in a sodium atom, it is 11, where atomic number Z is equal to the number of protons in the nucleus of an atom, equal to the number of electrons in a neutral atom. Mass number. The number of protons and neutrons present in the nucleus are collectively known as nucleons. The total number of nucleons is termed the mass number A of the atom. Mass number A equals number of protons P plus number of neutrons N. Isotopes. Isotopes are atoms of the same element that have the same number of protons but different numbers of neutrons in their nuclei. This results in variations in their atomic mass. For example, carbon-12, carbon-13, and carbon-14 are isotopes of carbon. Isobars. Isobars are atoms of different elements that have the same mass number, meaning they have the same total number of protons and neutrons in their nuclei, but different atomic numbers, number of protons. For example, carbon-14 and nitrogen-14 are isobars because they both have a mass number of 14. Isotones. Isotones are atoms of different elements that have the same number of neutrons but different numbers of protons in their nuclei. This results in variations in their atomic mass and atomic number. For example, carbon-14 and nitrogen-15 are isotones because they both have 7 neutrons in their nuclei. Isoelectronic species. Isoelectronic species are atoms, ions, or molecules that have the same number of electrons. This means they have identical electron configurations. isoelectronic species may belong to different elements and may be either atoms or ions. For example, the fluoride ion F minus, the neon atom Ne, and the sodium ion Na plus are isoelectronic because they all have 10 electrons. Some drawbacks of Rutherford model. So according to Maxwell's electromagnetic theory, a charged particle moving in an orbit is under acceleration and should emit electromagnetic radiation. As a result, an electron moving around the nucleus would lose energy and spiral inward, eventually crashing into the nucleus within 10 to the negative 8 seconds. However, this does not happen in reality. Therefore, Rutherford's model cannot explain the stability of atoms if the motion of electrons is described based on classical mechanics and electromagnetic theory. Also, Rutherford's model does not provide information about the distribution of electrons around the nucleus or their energy levels. Next one is developments leading to the Bohr's model of atom. Two major developments contributed to the formulation of Bohr's model of the atom. 1. Dual nature of electromagnetic radiation. Electromagnetic radiation exhibits both wave-like and particle-like properties. 2. Experimental results on atomic spectra. These results indicated that atomic spectra could be explained only by assuming quantized electronic energy levels in atoms. Next is nature of electromagnetic radiation, electromagnetic wave theory. This theory was proposed by James Clerk Maxwell in 1864. The main points of this theory are as follows. Radiant energy. Energy is emitted from a source, such as a heated rod or the filament of a bulb through which electric current is passed, continuously in the form of radiation, known as radiant energy. Electric and magnetic fields. The radiations consist of electric and magnetic fields oscillating perpendicular to each other and both perpendicular to the direction of propagation of the radiation. Wave character. The radiations possess wave characteristics and travel at the velocity of light 3 times 10 to the power of 8 meters per second. Next up is frequency. The frequency n, pronounced nu, of a wave is defined as the number of waves passing through a point in 1 second. It is expressed in hertz, where 1 hertz equals 1 cycle per second. Velocity. The velocity c of a wave is defined as the linear distance traveled by the wave in 1 second. It is commonly expressed in meters per second, m per s, or centimeters per second, cm per s. Amplitude. The amplitude a of a wave is the height of the crest or the depth of the trough. It is expressed in units of length. Wave number. The wave number is defined as the number of waves present in 1 meter of length. It is the reciprocal of the wavelength and is represented by nu bar, pronounced nu bar. Electromagnetic spectrum, see the image. Limitations of electromagnetic wave theory. Electromagnetic wave theory was successful in explaining properties of light such as interference, diffraction, but it could not explain the following. 1. The theory could not account for the observed distribution of radiation emitted by a black body. 2. It failed to explain why certain frequencies of light could eject electrons from a metal surface, while others could not, regardless of the light's intensity. 3. The theory could not explain how the heat capacity of solids varies with temperature. 4. It could not account for the discrete line spectra observed in atomic emission spectra, such as those of hydrogen. Next topic is very important: black body radiation. An ideal body that emits and absorbs all frequencies of radiation perfectly is called a black body. The radiation emitted by such a body is known as black body radiation. The exact frequency distribution of the emitted radiation depends solely on the black body's temperature. At a given temperature, the intensity of radiation emitted increases with a decrease in wavelength, reaches a maximum value at a specific wavelength, and then decreases with further decreases in wavelength. Planck's quantum theory. To explain the phenomenon of black body radiation and the photoelectric effect, Max Planck introduced Planck's quantum theory in 1900. This theory was later extended by Albert Einstein in 1905. The main points of this theory are as follows. I. Radiant energy is emitted or absorbed in the form of small packets of energy called quanta. The energy of each quantum is directly proportional to the frequency of the radiation. The theory introduces a proportionality constant known as Planck's constant, denoted by h. Its value is 6.626 times 10 to the negative 34 joule seconds. Photoelectric effect? In 1887, Heinrich Hertz discovered the photoelectric effect. He found that when a beam of light of a certain frequency strikes the surface of some metals, electrons are emitted or ejected from the metal surface. This phenomenon is known as the photoelectric effect. Spectrum. When a ray of white light is passed through a prism, the wave with shorter wavelength bends more than the one with a longer wavelength. Since ordinary white light consists of waves with all the wavelengths in the visible range, a ray of white light is spread out into a series of colored bands called spectrum. The light of red color, which has longest wavelength, is deviated the least, while the violet light, which has shortest wavelength, is deviated the most. Line spectrum of hydrogen? See the figure. When an electric discharge is passed through hydrogen gas enclosed in a discharge tube at low pressure, and the emitted light is analyzed by a spectroscope, the spectrum consists of a series of lines grouped into different series. This is known as the hydrogen spectrum. Calculations in the image. In 1890, Rydberg proposed a simple theoretical equation for calculating the wavelengths and wave numbers of the spectral lines in the different series of the hydrogen spectrum. This equation is known as the Rydberg formula or equation. Next is Bohr's model of atom. In 1913, Niels Bohr proposed a new model of the atom based on Planck's quantum theory. The main points of this model are: electrons revolve around the nucleus in certain definite circular paths called orbits. Each orbit is associated with definite energy, and therefore these are known as energy levels or energy shells. These are numbered as 1, 2, 3, 4 or K, L, M, N. Only those energy orbits are permitted for the electron in which angular momentum of the electron is a whole number multiple of h over 2p. Angular momentum of electron, MVR, equals nh by 2pi, n equals 1, 2, 3, 4, etc., where m equals mass of the electron, v equals tangential velocity of the revolving electron, r equals radius of the orbit, h equals Planck's constant, and n is an integer. While an electron is in a particular orbit, it neither absorbs nor loses energy. Its energy remains constant. When energy is supplied to an electron, it absorbs energy in fixed amounts, quanta, and jumps to a higher energy state, excited state. The excited state is unstable, and the electron may return to a lower energy state, emitting the same amount of energy. D equals E sub 2 minus E sub 1. Limitations of Bohr's model. The theory could not explain the atomic spectra of atoms containing more than one electron. Bohr's theory failed to account for the fine structure of spectral lines. The theory could not satisfactorily explain the Zeeman effect, splitting of spectral lines in a magnetic field, and the Stark effect, splitting of spectral lines in an electric field. Bohr's theory did not provide an explanation for the ability of atoms to form molecules through chemical bonds. The model was not consistent with the Heisenberg uncertainty principle. Dual behavior of matter, de Broglie equation. In 1924, Louis de Broglie proposed that matter exhibits dual behavior, meaning it shows both particle-like and wave-like properties. According to de Broglie's hypothesis, just as photons, light particles, have both momentum and wavelength, electrons also exhibit these properties. Heisenberg's uncertainty principle, see the image, quantum numbers. Atomic orbitals can be specified by giving their corresponding energies and angular momentums, which are quantized. That is, they have specific values. The quantized values can be expressed in terms of quantum number. These are used to get complete information about electron, that is its location, energy, spin, etc. Principal quantum number, n. It is the most important quantum number since it tells the principal energy level or shell to which the electron belongs. It is denoted by the letter V and can have any integral value except 0, i.e. n equals 1, 2, 3, 4, and so on. The various principal energy shells are also designated by the letters K, L, M, N, O, P, starting from the nucleus. Shapes of s orbitals. S orbital is present in the s subshell. For this subshell, I equals 0 and m I equals 0. Thus, s orbital with only one orientation has a spherical shape with uniform electron density along all the three axes. The probability of one s electron is found to be maximum near the nucleus and decreases with the increase in the distance from the nucleus. In 2s electron, the probability is also maximum near the nucleus and decreases to 0 probability. The spherical empty shell for 2s electrons is called nodal surface or simply node. Shapes of p orbitals. P orbitals are dumbbell shaped and are present in the p subshell where L equals 1 and M1 can have 3 possible orientations, 1, 0, plus 1. There are 3 p orbitals, px, pi, pz, oriented along the x, y, and z axes respectively. The electron density is high in the two lobes, with a nodal plane passing through the nucleus where the probability of finding an electron is nearly 0. Shapes of d orbitals. D orbitals are present in the d subshell where L equals 2 and M equals -2, -1, 0, +1 and +2. There are 5 d orbitals, each with distinct shapes and orientations. Aufbau principle. The Aufbau principle states that in the ground state of atoms, electrons fill orbitals in order of increasing energy. Electrons first occupy the lowest energy orbital available and only move to higher energy orbitals once the lower ones are filled. The general order of orbital filling is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5, s4d, 5, p6, s4, e for 5d, 6, p7, s5, f6, d in 7p. Pauli exclusion principle. According to the Pauli exclusion principle, no two electrons in an atom can have the same set of 4 quantum numbers. This principle can also be stated as only 2 electrons may occupy the same orbital, and these 2 electrons must have opposite spins. Electronic configuration of elements in ground state, see the image. Thank you for watching. We will be dropping notes in the description of this video. If you found this video helpful, kindly like, subscribe, and share. See you in the next video. All the best for your exams.